Welcome again. Well, we have a little reboot here today to talk about this project. It's called the Level 3-4 ICMV evaluation. Kind of look very coded title, but we're going to talk about more in depth. So first I have to acknowledge NRRA to sponsor this research. So I'll give a quick intro of myself. I'm George Chen with the TransTech Group in Austin, Texas. I have to say good morning, good afternoon, and good evening. I know some of you may be logging in from other countries. This is a project that Sohail and I have been working on since last year. Sohail, up to you.
Good morning, all. It's a pleasure to be here.
Wonderful. As you can see in the middle, in the bottom of the middle, we have the logo of ISIC. So that's the International Society for Intelligent Construction. So this is kind of co-sponsored by the ISIC to provide our support always to the NRA activity and initiatives. So let's get into this project. So this is the outline what we're going to cover today. Firstly, we will give you a project overview, what this project all about, why we're doing this project, and what it's for, what we try to accomplish. Then we're going to decode the level 1, 2, 3, 4, 5, so-called the classification system of ICMV. It's a very, very important so-called roadmap by the Federal Highway published back in 2017. Then we're going to get into what the level 3 and 4 ICMV prototype that we're currently building, and the status of the component as well as the prototype, working prototype. Then Sohail is going to cover very detailed in field validation what we're going to do in the field projected next year using those prototype in a test project at one of the project MnDOT, and what field tests we're going to conduct, including the field instrumentation and data processing, and also using the super duper model from the NCHRP research product to aid and help interpret and evaluate the project. And finally, we can give you what we try to accomplish in the next about a year and a half. So project overview. So this project is the NRRA project. The entire project title is called, kind of wordy, mouthful, Evaluation of Levels 3 and 4, Intelligent Compaction Measurement Values, ICMV, for soil, subgrade, and aggregate subbase. So that have a very defined scope for this study. So this will be focusing on the soil subbase and aggregate subbase compaction, not the asphalt. So the logical step after this project will be evaluate those high level ICMV for asphalt compaction. So this is a 36-month project. The outcome from this project is to provide independent evaluation on the prototypes of level 3 and 4 versus 1 and 2. Just bear with me for now. We're going to explain what this level 1 all the way to level 4 is all about. So this will be an independent evaluation by Sohail and I, and working with a lot of research partners that we're going to show you a little bit. And very important outcome for this project will be a blueprint for future certification procedure for IC. This is something that's lacking right now, as many agencies, not just in the US, but around the world, have been using IC data for acceptance or for pay adjustment. So it's very important to have a procedure to certify the system so the data can be accepted. So that's kind of our overview of this project. And we do have a very powerful, very versatile research team that include, so MinDOT, we have Lois and Rebecca as our project manager and technical liaison. We have a panel of John Sigmeyer, Jordan Nail of North Dakota DOT, and Irvin from Matthew Construction. Our research team include me and Sohail, as well as several researchers. I'm going to show you in the structure later. Very importantly, this won't happen without our industry partner to provide us rollers and also the prototypes of level 3 and 4 ICMVs. So we'll thank Caterpillar to provide our support, and also MOBA and SCMG to provide us the prototypes, and also Syncor to provide the module for the integration. So this is our research team structure, started with Lois and Rebecca, and then we have, so me and Sohail will be PI and co-PI. Then we have very experienced IC researcher, Amanda Gilliland, Sergio Abbas, and also Pramich. Now we get into the decoding of ICMV. I got asked this question all the time. So what is level 3 and 4? What is 1 and 2? What is it all about? So this all come back to the core of the intelligent compaction technology invented 40 years ago, to be exact, 44 years ago, in 1976. So over this core technology is the measurement system. There are many different measurement systems in the market developed in the past 40 years. They're called different type of names. So during the Federal Highway IC project back into about a dozen years ago, we use in generic name, it's called Intelligent Compaction Measurement Value, ICMV, to cover all the different technology and product that use the accelerometer-based measurement system. So it's the accelerometer mounted at the center of the axle of the front drum, normally front drum, vibrating, and then the rebound, a signal acceleration, would be through the control system using different kind of model and produce the ICMV. And for many agencies to use this as a quality control tool or acceptance tool, it had to be correlation with the material modulus and density and other spot tests with the compacting material. So those kind of feedback loop to ensure ICMV is measured what it's supposed to do. So here's the inconvenient truth. To get the ICMV, it's a very complex process. And this, depending on what kind of model you use, it can be affected by the top factors, which is from the roller itself, and the bottom factors from the material being compacted. So the top, including the roller vibration, eccentric forces for vibration, the amplitude and frequency for the vibration, and speed also affects certain ICMV of the some model. So that's the factor we need to keep in mind when we develop or use ICMV or interpret the value of ICMVs. On the bottom factors, that's the soil types and moisture content. It's very important to how the ICMV being interpreted, and the mixed proportioning for the asphalt, temperature of the asphalt, and very importantly, the support condition. So the last factor, support condition, is very important when using the level 1 or level 2 ICMV, because they are affected by the supporting layer. There are also other challenges. So to measure anything in a static mode is fine. But once you have the instrument on the vibrating roller, it has a lot of implications and complexities. So first factor is vibration force is not equal to compaction force. So that have to be recognized when any manufacturer or researcher get into ICMV development. And another one is the actual strain measurement is different from the theoretical computation. So theory is not always matching the field condition. So that's a very important factor to recognize. So any theoretical development by ICMV had to be validated in the field. That's what this project is all about. Everything look good on paper, we'll make sure it is to be validated in the field. And then the C, which is very important when decoupled or when during the later stage of compaction, the roller often get into a double jump mode, which is because the compacted material getting stiffer and the reaction force make it to bounce in the air between cycle of vibration. So that's when most of the ICMV model fail. And the model have to consider the bouncing of the drum. So that's a lot of obstacle to overcome. That's why it took 44 years to get to what we are today. And in the early days, especially in the 90s, when agencies started using ICMV, and at that time it's a level 1 ICMV, and they started to come into issues of correlation with the spot test. The correlation is very poor due to a lot of different factors we're going to talk about. And over the years, there are all kind of different type of ICMV, and that really caused some confusion for the users, not only users, but also agency, industry, contractor. So what ICMV is all about and what difference they are. So in 2017, Federal Highway had published the ICMV roadmap that systematically defined the different type of ICMV from level 1, 2, 3, 4, and 5 with a very stringent criteria. So here's the thing. The level 1 or 2 ICMV is using empirical solution based on frequency ratios. And level 2 is using energy method on rolling resistance. So those are, which I will show you shortly, that have some limitations. And level 3 ICMV is a great advancement, I think the early 2000, the mid 2000, when they started using mechanistic solutions on static or dynamic method. And the outcome of the ICMV is in stiffness, reaction force, or modulus, much more comprehensive and easier for the user to correlate to the spot test. And then level 4 and level 5 ICMV, just another level up. Level 4 can really produce a reliable ICMV when it's in double jumps. And level 5 ICMV is the holy grail that can produce anything you want in density or modulus. So that's kind of roadmap that the Federal Highway ICMV have laid out. So here's a very important criteria here. There are 4 criteria to classify an ICMV. Firstly, it's the correlation between the ICMV and in situ spot test. We're not going to get away with spot test any soon. So the spot test for acceptance are all deep embedded in the acceptance specification of compaction for agencies from all around the world. So the correlation is very important to build up the confidence between the 2 values, ICMV and spot test. And the acceptance test is R equal to 0.7. It's been a criteria for most of the specification around the world, including those in EU. There's an EU standard, and most of the European countries have been using similar standard, and also the Chinese railway space compaction standard. So the term converted to R, so R squared. So that's miss the square here. R squared is 0.5. So R equal to 0.7. So that's a minimum requirement. Then the second criteria is whether the ICMV can provide reliable value when it double jumps. And then third is another holy grail for ICMVs, whether it can produce a layer-specific ICMV value. So you can separate from the top, from the bottom layer, and that's one of the contributions from the Sohail's and NCHRP project, and also other vendors have get into that area. And then finally, advanced IC, the ICMV cannot really use a model to solve the world peace, so you have to combine with advanced technology such as AI and the auto feedback system. So here's the table, a big table. You can look it up from the Federal Highway website, from the ICMV roadmap publication. So what we have right now is we literally from the yellow arrow on the left, we currently have 1, 2, and 3. We're barely getting to level 4, right, as we are right now. And on the right-hand side is all the criteria for correlation, for decouple, or layer specific, or whether it can combine with AI for future development. So very important, really boundary is the level 3 here, because level 3 using different kind of model and produces stiffness, coefficient, resistance forward, and modulus. So those are very important, I would say, advancement of ICMV. And then we can get to the next level to get into more related, the measurement we can relate it to the mechanical property of material. So that's a very important direction we're seeing here. So let's go back all the way to 44 years ago. So this is the first generation of ICMV, which is using empirical reacting model, using the acceleration measured from the accelerometer mounted on the axle of the drum. Then once you look doing the frequency analysis, you can observe the different peaks and different frequency related to the stiffness of the material. So that's the quite a very, I would say, inventive, groundbreaking finding at that time, because you can now measure the property while compaction instead of waiting until everything's finished. So this is very, very important find. And you can see the peak is different in different frequency. So different ICMV values such as CMV, compaction meter value, the HMV, harm meter value, and CCV, the compaction control value. All these are using a similar approach using the frequency responses. And the level 2 ICMV is using energy model for the friction, for the rolling resistance. One such model is MDP, the machine drive power. And that, so this method is unlike others that is not based on the accelerometer-based measurement system. Now come to the level 3, which is big advancement in the early 2000s. So this one specific model is using discrete model. Can go back to the fundamental mechanistic model with the dashpot and the spring with the mass and the drum and the frame. So using that to back calculate the property of the compacting material. So, example of such a level 3 ICMV is KB value, so-called soil stiffness value, or EVI value, a vibration modulus, and Sanko level 3 solutions. Now we get into level 4. Level 4 is another breakthrough, which is the model of the previous solutions would be invalid when it's in double jump. And this model is called collision impact model, will take care of that. So that's a very important model that can back calculate based on the acceleration and the speed and the displacement to evaluate what the stiffness of the material during double jumps, as well as non-double jump. Our ultimate goal is to use the level 4 ICMV to combine with the AI solutions the AI is really to train a system from all the database, difficult material, different gradations, different support conditions, different moisture content, you name it. So that will help to fine tune the theoretical model and make it better. The NCHRP 2445 is a kind of have an initial attempt for that. And using this kind of system have a great impact, which means you can build everything from the ground up, and you can have the mechanical property for each of the individual layer. All right, so we'll get through the medicine of classification of ICMV. The reason we're pushing for level 3 and 4 is we have difficulty with level 1 and 2. In the 90s, when Chinese using the level 1 ICMV, they are firstly got excited and have a very low correlation spot test with the level 1 ICMV. That really form a big hurdle until the level 3 and 4 ICMV come up. And in 2012 and 2012, when MnDOT started some soil IC specification, they also run into the same problem because most the ICMV at that time is all level 1 or level 2 ICMV. So it's really important for us to have an independent evaluation and push and validate the level 3 and 4 ICMV and push the higher level. So in this study, we'll be using a Caterpillar single drum roller with the level 1 ICMV, CMV, and maybe level 2 MVP as a comparison. And will be mounted on those roller with other ICMVs. And another roller we're going to use would be the XCMG single drum roller with a level 3 and 4 ICMV prototype. That's why the gray fine line between 3 and 4 is there, because the roller information can be all provided to the level 3 and 4 module in the OEM system. So it can break to the barrier to the level 4. So that's what we call it 3 and 4. Another one that we will be working with is the mobile IC retrofit system. So it's an aftermarket retrofit system that will be integrated with the level 3 ICMV module. So the prototype dimension would be mobile IC retrofit system with a SignCore ICMV module. And we're also going to be using the OEM IC system from XCMG that will be prototype integrated with the SignCore ICMV. And then very importantly, the UTEP from Sohail's team will be provide us a DAQ system from the NCHRP's 2445 study that have been calibrated with numerous field study, and they have a 3D Ares Dyna model that built out a lot of database to train the AI. Sohail going to talk about some detail later. So I think we have everything here to do a mini rodeo. To get into more detail about what the level 3 and 4 ICMV module is. So this is the module that I'm talking about. They're using a accelerometer and have a circuit board that built in the model to calculate ICMV in real time. So software is computation too slow. You have to be using the hardware to do that. So here's the current ICMV module. You can see here on the module on the left and the connector on the right. So this has been redesigned with the high-speed triaxial accelerometer. I think due to the COVID-19 delay, it's a blessing in disguise. Give us the opportunity to work with our research partner to improve those accelerometer and then the entire system. So the accelerometer are free of influence from Earth's gravitational acceleration signal, have about probably 3 to 4 times of the maximum frequency of the roller vibration. And this should do a very good job for supporting level 3 and 4 module. So what the input and output of this module going to be the roller parameter, including this, the dimension, the weight, eccentric weight, and also the acceleration from the accelerometer. For asphalt, you can have a temperature sensor to input. So this SignCore IC module have a built-in circuit board, can output the resistance force, or the stiffness, or modulus, or all three. So it will output those mechanical properties that we can compare with the UTEP NCHRP DAQ system. So here's what it looked like, that all these different roller, i.e. OEM or retrofit, will be integrated with the SignCore and then integrated to that system. All right, now we have our prototype. The next is to make it work and evaluate it independently in the field. So off to you, Sohail. Just let me know when to advance the slide.
Yes, sir. Good morning, all. What a pleasure to be with you today. Okay. Essentially, our role over here is to validate the measurements that we get from the rollers, different rollers that George discussed. So essentially what we are discussing is have a test site, and what we are requesting is around 25 feet. 25 feet is 2 lanes wide, so that we have enough lateral distance to maneuver, and at least 250 feet of area that we would use very carefully with the rollers to evaluate the stiffness of the system. We start with testing the subgrade, and shortly after, the base will be placed and compacted on top of it, and we're going to remap it again so that we can do the analysis.
So just chime in here, Sohail. So we'll be tested in the field in 2021 in at least one or maybe 2 test sites in Minnesota. Go ahead, Sohail. So here you have to unmute yourself.
I mute myself, sorry. Okay. Okay. So we have a detailed field schedule and activities. We have perfected it over the dozen sites that we have done it for the last few years. And basically it starts with, I'm not going to go through every detail, but we're going to start with the coordination and initial setup a couple of days before. It's very important the contractors, the DOTs, and the research team, as well as the roller operators, know exactly what we want. We're going to do a scenario play, make sure that everybody knows what they're doing. We're going to test all the equipment to make sure that everything is in order, everything is working. The first test would be on the subgrade, and we allow the layer of subgrade be prepared. We install geophones at several depths inside the subgrade. The geophones are some three-dimensional, so that we can capture the horizontal and vertical motion of the roller as it approaches. We're going to map the subgrade, and after that, we're going to conduct dense lightweight deflectometer and dynamic cone penetration test, very dense, along with conducting nuclear density gauge and get moisture samples to verify that nuclear density gauge moistures are okay. When we are talking about testing in that 250 feet, we are talking about over 40 tests, because we need to exactly map the variability in a large number of parameters at the site. as soon as that is done, we are hoping that the base would be provided, compacted, and then we're going to embed more geophones inside the base, retrofitted, and then we would map with the IC rollers one after the other on top of that on-bound aggregate. And then we repeat at the exact same points that we ran the lightweight deflectometer and DCP on the subgrade. We just use a rover to identify them precisely and run the test again. And once again, we run nuclear density gauge and take moisture sample so that we can map the variability of the two layers. There will be very high precision GPS units, one sitting next where the geophones are, and the other one would be on top of the roller. These are independent from us. And what the reason for two GPSs is to use the time and coordinate the timing so that we know exactly where the roller is relative to the geophones so that we can map it. So essentially, the steps in the field is just after the subgrade is prepared, we install the geophones, map the subgrade surface with the instrumented IC roller. We conduct extensive modulus space testing and moisture testing. After that, we spread and compact the unbound aggregate base. We install the geophones in the base, map the surface of the base, and then we again repeat all the testing. And then we just proceed with all the data to both statistically and numerically calibrate the results. Next one. Okay, so essentially, you have to be careful when you are doing intelligent compaction. You have very spatially very rich data, but if you look in terms of the depth, you have one piece of information, so you have to be careful what you're trying to extract. So by mapping on top of the subgrade after it's ready, we just get a equivalent modulus down to a depth of embedment of the depth of influence of the roller, and that depth of influence is basically essentially ascertained by the geophone measurements. And after you construct the base, and if you match the ICMVs from the before and after, we can then provide the properties and modulus of the top layer and an equivalent modulus for the software. So that's what we have done in NCHRP 2445. I encourage you to go to that report. It's out and came out last week, actually, the official one. So please study that if you're interested. Okay, what we have around 2013, we were working on the everyday counts 3, I believe. And as part of that, we had a project with Federal Highway Administration to understand what it is that the intelligent compaction rollers are measuring. To understand better, we needed raw signal, and we developed a system that you see over here. And basically what we do, we mount an accelerometer on the roller. Actually, we do one on each side, and you see on the left bottom picture how the accelerometer is measured. Our goal is to get accurate, highly calibrated system and get the raw data. Our goal is not to be a provider of equipment. These are just for research grade equipment. These are not for like Syncor for commercial development. The geophones that I talked about burying into the ground, there are 3D geophones, and basically we drill a hole and with minimum disturbance, and we install them at different depths, as you see over here. And then we have a computer and a data acquisition system, and conditioning and everything are in this box that you see on top, on data acquisition box and the laptop. The quality control, okay, so these are some of the pictures of instrumentation. We just, again, drill a hole, just take the accelerometer and put inside the hole with the right orientation, bring the cables and put it in the box over there on the side so that, you know, it will be protected, and we make all the measurement. This is the field instrumentation installation. You have to be careful that to put the material back as well as you can. Go to the next one. This is basically shows you the setup. You see that this is Sergio over here. He's the master of putting all the system together. He's our instrumentation electrical engineer, and he's sitting over here observing the location of the geophones while there's a GPS next to him, and there's a GPS on top of the roller. We are just mounting, this is the accelerometer that comes with most of the existing systems, and our accelerometer is mounted on the roller as well. You see two of them, you see over here. We usually have one on this side, the other one on the other side to consider the movement, uneven movement of the roller. Go to the next one. So what do we do with all the data from the geophones? One of the data, the reason is to just get the output of the systems and compare it with the models, theoretical model, and the measurements. So what we would do, we would use laboratory testing to get the property of the soils, nonlinear property of the soil, because under compaction, you put nonlinear stress, it generates nonlinear stresses, and the soil goes nonlinear. We would basically model using a final element code, again, described in 2445, to see what the deformation was at that point with distance, and then we compare it with the field, and are hoping to get a systematic error, as you see, so that we can calibrate the models. The calibration of the model is very well documented in the work that we did with one of my colleagues, Mehran Mazari. And that has to do with the discrepancies between the field and the laboratory, because the compaction in the field is different. But it's been shown many, many times that it's systematic, so we can basically come with a calibration. After we calibrate the system and we go ahead, and after we got the model calibration, we go to the next step. Show the next slide, please. Just one back. We go ahead, and I told you we run more than 30 tests on a grid over here at the site, so that with the LWD and DCP, and knowing the moisture, we go ahead and do a calibration of the model, local calibration of the model to the soil, which would be the next step. So basically, this case shows you the calibration of the model with the local calibration with 4 or 5 points with different LWD moduli. We come up with a calibration, local calibration, and then for all the data at the site, we go ahead and we start predicting the modulus using the ANN, and that shows you that within 10, 15, 20%, we can estimate what the modulus of the layer would be, at least based on the about 6 or 7 sites that we did it as part of 2445. The next one, please. You want to go over that, or you want me to go? George, you want me to go or you're going to go?
So let me cover this part then.
Okay.
So what Sohail have just described, going to be tons of data, and really high quality data. That's what we're aiming for. That really learn from not just the NCHRP study, but all the IC study that Sohail and I have conducted for the past decade, more than a decade. So those data will be processed using the raw data as well as the process data, so we can do the correlation and evaluate the 4 criteria. In this case, probably 3 criteria that inform the ICMV roadmap from the federal highway. Correlation with the spot test, whether it can produce ICMV during double jumps, whether it can provide layer-specific properties. So those are the 3 criteria will be evaluated using those statistical analysis, correlation analysis, and also compare with all level ICMVs. So what I've been seeing, what we're just showing on the integrated model, those were provided level 3 and 4 ICMVs. With the extra roller that we're going to be using, that would be provide level 1 ICMV. In fact, Sohail's DAQ system from NCHRP 2445 can be used to calculate level 1 and level 2 ICMV just using the model, and they've been very well validated against the commercial level 1, level 2 products. So we're going to have a rich data from the field test, including those measurements from the rollers with level 1, 2 system, and level 3, 4 system, as well as the DAQ system from UTEP, which is really a prototype of level 5. So we will do a very thorough comparison and evaluation to verify whether the level 3 and 4 prototypes have met the criteria that in the ICMV roadmap published by Federal Highways. So that's a very important one. So this study will provide a very neutral, independent evaluation from all the way from level 1, 2, 3, and 4 ICMV data to the world. So the final report will be a framework for future certification program for single drum ICMV rollers. What the test site requirement, the dimension, the material, the layers. So that would be outlined in this framework. And also the IC roller system requirement will be also in there. And plus the spot test requirement requirement. So the framework will provide really all the components that you normally need for AASHTO standard, for example. And then based on the study that we're seeing here, we'll be looking hard on the requirements for the correlation again between ICMV and spot test from the test strip for IC specification. So the 0.7 R, the R equal to 0.7 criteria being used for about 2 decades. So here will be another critical review for the requirements. And because the previous requirements are based on level 1 ICMVs. So here, based on the extensive study here, we may establish the minimum requirement for the correlation for different level of ICMV. So the agency can pick and choose what will be best suited for their IC application. And another very important metrics, which is not being covered by most of the IC spec, is the uniformity metrics. What uniformity metrics should be used for ICMV? And either using standard deviation, variance or so-called the semi-variogram. So that will be heavily evaluated here, which metric will be more suitable for future specifications. And we'll provide some recommendation for that. And some uniformity metrics using around the world, and sometimes often just based on a line measurement from pass to pass to see the variance. So that probably not really of uniformity, it's more consistency metrics. So we'll provide all these report requirement and measurement requirement for IC specification, including certification and qualification, as well as for the operation for production type of compaction. And very important product from this research will be proposed companion acceptance test. What the spot test would be more appropriate compared with conventional spot test, which is now normally based on nuclear density gauge testing. So the likely candidate acceptance test will be LWD and the DCP and others. And finally, we're going to have a white paper that for standard or reference roller. What that means is for facilitating the future IC certification or qualification, you cannot rely on just one DAQ from UTAP. So it could be just similar to the reference profiler for high-speed inertial profiler certification, that in here, the analogy will be using a reference or standard roller. Could be not a roller, maybe a mini roller or something that's smaller devices. It's sort of analog to the moving plate load test that can be used for facilitating the certification in the future. So the outcome will be a framework, but all the detail will be gradually filled in for future research, including those highlighted in the white paper we're going to be using. Any other you want to add, Sohail? In terms of final?
Oh, no, I'm good. You know, you did a good job. We look forward to get the data and share it with everyone. Yeah,
I can't wait, Sohail. We've been waiting for so long to get this prototype done. And I really looking for this very, very extensive. It's more like the past research, like NCHRP on steroid. Because the past research normally used in level 1 or 2 ICME. Now we have everything from level 1 all the way to level 4, plus all the super duper in field instrumentation, and also the ANN model from the NCHRP study. So I'm really excited. So talk about this, what we're going to do in the next year or two. We're going to finish for about 18 months from now. So the integration for task 2 should be finished right before we do our field validation. So we're probably going to finish before July 31st, 2021. As we speak now, the integration is in the final stage of integration and testing. So we should be able to finish that much earlier than July 31st. And then the instrumentation and field test should be completed by October next year. But consider the weather in Minnesota, we should finish by the end of summer. Then we'll start to do the data processing, analysis, and really critical review and finish report by June 30th, 2022. So if you look at where we are now, we've come a long way. It just took a long time for us to work with all the different parties, industry partner, components, redesign, and then integration So what we're here is September, end of September 2020. So we're shooting for the start of the field evaluation from May next year all the way to September to see what it depends on what when the prototype will be field ready and shipped to the field site and so ready for the field testing. So that will take a lot of coordination work between our research team and our research partner, industry partner, as well as a MinDOT project management selections. So that's pretty much our task schedule. So the final slide I would like to highlight is ICMV roadmap. You can see that big whoosh arrow here. It really come a long way from level 1 all the way to level 2 or 3. It took about 20 years, and to level 4 another 10 years. So hopefully we can achieve level 4 and 5 in another 4 or 5 years time. And the bottom is a link to the ICMV project webpage on the MinDOT website. You can take it out, check it out, and check out our progress. Lauren, now we are ready to entertain any questions.
Okay, maybe Sohail, if you do have one question in the Q&A box, I haven't received any other through the chat, but you guys should be able to see that as well. Maybe Sohail.
Hey, Lauren, your voice is very soft.
Yeah.
We do have one question in the Q&A box. I didn't receive any through the chat. Are you able to take a look at that?
I do not see, Lauren, a question. Sorry, I'm in the chat, but I don't see a question.
Okay, it should be in the Q&A. That should be at the top. You just have to drop down. I guess I can.
Yeah, I saw that.
Okay.
Yeah, let me read it out so Sohail can help answer. So the question is, Dr. David White from InGeos Geotechnics have been using the automated plate load test to accurately calibrate IC rollers for several years. Would you comment on what level 4 or 5 ICMV development add to what Dr. White already has in use? Sohail, go ahead.
Well, Dr. White has a very nice system, and since he's a private person, his system is proprietary, and it will be difficult for the DOTs to specify proprietary information. What we are doing, we are essentially providing an open source verification and calibration system so that the DOTs can do on their own with any consultants or in-house force that they desire to use.
Yeah, to add to what Sohail just said, just like what we did for the EDC2 IC study, and the following IC retrofit study with Sohail and I, and then the NCHRP 2445 report is very extensive. All the data, all the result, model development, validation, all been transparent, well documented. So that's our approach for this project, is provide the precious field data independent evaluation to the world transparently. It's very important for agency to see those data firsthand instead of using commercial product as a black box.
Did we answer your question?
Richard Gizo? Yeah, he's from Alaska. It's still early there.
Okay, no problem.
Yeah, he won't be able to answer, verbally. So, If anyone else has any other questions, I haven't seen anything else.
All right. Well, as I mentioned, Lauren had maintained a very good website for all the NRA research, including this project. So check it out there. I will provide more update of this research on the webpage. So look forward to the prototype completion and the field test in 2021. And Sohail will be sharing with you results as soon as we have process and come out from this study. Excellent. Ben, do you have any final words?
I guess my final words is thank you, George and Sahil. Look forward to the final product that you're developing for this. So thanks again for your time today, and impeccable timing since we're right on 30 minutes.
Excellent. Well, thank you, Lauren, for coordination of this project update. And also thank for all the people who have logged in from all over the world. I know there's some from European countries and some from Australia to log in. So thank you all.